Good afternoon, everyone. My name is Shiva Kasiviswanthan. I'm a principal applied scientist at AWS. Me and my team are working on developing AI agents for monitoring and observability for large-scale cloud operations. And today in this talk, I'm going to share some broad research directions that we've been exploring to make agents more adaptive. So I think, let me start with, today's agents are already pretty capable, right? So we all know that how good they are good at planning, tool execution, retrieving information, iterating over the solutions to solve complex tasks, right? But as these agents get deployed in more mission-critical applications, we in AWS believe there are some critical research questions that need to be solved because they can be widely deployed. And here are some of them that we have been exploring in our team. The first question that we've been exploring is this question of how should agent allocate computational resources, right? Imagine that you have a fixed computational budget and you want agents to best utilize that computational budget to solve the problem at hand. The second question is along making agents reason better, right? So agents needs to be able to explore multiple reasoning paths to make decisions in a more efficient fashion. And the third research question that we've been exploring is the question of how do we evolve agents over time, right? So the agents are not static pieces, but that's continually adapt over time to make and learn how to solve the tasks over time better. So in this talk, I'm going to just focus on the first two tasks, but I'll just briefly end up with how we are looking at the third problem at the end. So let me start with the direction one. So this is the notion of budget-aware adaptive execution, right? So today, if you look at most agents, they have a fixed execution policy that you define using a prompt or some other local heuristic, right? I guess what our goal is to make these agents learn these execution policies. So the agents can learn over time these execution policy so that and then they decide how these policies are then executed. And then you also have notion of a computational budget. You want the agents to work best under some computational budget, right? So abstractly, you can think of this as a problem where you have some context. The agent has some context. And it is to decide the best next action to do. The action could be retrieve information, use the tool, verify the results, update memory, whatever. There is some action space. And the important constraint is that there is notion of budget, right? I mean, so there is a budget that the agent has, and it has to respect that budget while executing these tools, right? So again, if you think of this a little bit more, I think this can be phrased as in terms of a formulation, we can be phrases as a constrained Markov decision process. And we've been using this framework to learn these policies, right? So again, the goal is to maximize some kind of expected utility under some notion of subject to some computational budget, right? Again, the budget could come from latency, cost, token, or whatever you want to think of, some notion of budget. Right, and does it work? And yeah, the answer is yeah. I mean, we've been have some success in implementing this. So what we've been showed that this plot, on the plot on the right-hand side, shows these adaptive agents learning better execution policy than using a scale-rise reward model, which is commonly used in practice, right? On the other plot on my left side is showing that it's also more sample efficient, right? So you're reaching the same competence using fewer iterations. So the amount of samples you need to get to some level of competence is significantly lower if you use these kind of adaptive execution policies, if you learn these adaptive execution policies. Okay, the second direction that I would just briefly want to talk about is notion of parallel reasoning, right? So today we have these agents, or at least these models, which are following a single reasoning path, right? And we have been exploring ideas that allow models to explore multiple reasoning paths in parallel. So these parallel paths are kind of learned during training and not during inference time. And then they are coordinated to select one path, right? So the answer is one. So there is some coordinated reasoning that happens at the end, which takes these multiple reasoning paths and produces one answer. And again, we have been implementing these ideas and testing it on benchmarks, and both over mathematical reasoning and coding benchmarks, we have been getting consistently good results. These are some results on some maths and coding tasks, and you can see the results for pass 1 to pass k. We have been getting better than very strong baselines. And especially the results are impressive on k equal to 1, which is the first when anyone gets one result out. Okay, so I'm almost out of time, so I just want to finish by going back to the research questions that I was interested in. So we have been, I just mentioned about this budget-aware adaptive execution, where the goal is to learn an execution policy that's adaptive and best uses the constraints it has. And then the second question of a parallel reasoning, where you're trying to generate agents to have multiple reasoning, so that multiple reasoning paths, so that they explore multiple paths to solving the same problem. The third question that we have also been focusing is this notion of continual model or agent adaptation. Again, the goal is to come up with principled post-training schemes that can adapt to new tasks. The main challenge there is to make sure that when you learn the new task, you don't forget what you learned previously, right? And we believe that these kind of solving these kind of three research directions will help us to generate the next generation frontier agents. Thank you.